All right, let's go. We're going to talk about this. Yes, I'm doing a video. You'll be in the video in the background. All right, so let's have a look. This assignment, you'll find these online. There are 2 sheets. There are 2 versions, so don't just automatically look at the one that you have that I get back to you or that you picked up in the class. There are 2. If you go into the drive, you will see here's our Unit 8 stuff. I'll send you the link. Go into Skill Drill. Here it is, BQ8.3. It's designed for sketching reflection, but we'll actually go through everything from this. Notice, here's one, here's the other. There it is. So the first one we're going to do will actually be the one that has water and air, and the ray is often up and to the right. The other thing you will need a protractor, and you will need your reference table, maybe some indices of refraction here. Page 2. Okay, let's go. First one. The assignment is to draw reflections, so let's start with that. If this were a reflection, that means that it came from the water and it's going to stay in the water. Can't go anywhere without your normal line, so set your protractor up. You may want to pause as you go. I'm going to try to move through a little bit quickly. And so here, I'm going to put a normal line right through my 90, all the way through the boundary. Normal is, of course, make-believe, so dash it. There it is. Now, we have right here a reflected ray because it is moving away from the boundary. We need the incident ray. So we need the angles here. Bring your protractor back. Right here, we have our angle of reflection. Do not trust your subtraction. Count. 10, 20, 30, 40. 1, 2, 3. Mine looks like 43 degrees. That's from the Smart Notebook protractor. Yours may be a little bit different. That's the angle of reflection. The angle of incidence then, following the law of reflection, will also be 43 degrees. If it's reflecting within water, well then it started in water. It started on the other side of the normal. 10, 20, 30, 40, 1, 2, 3 degrees away. I don't have to turn my protractor, but you do. So, let's put one of these in here. This is an incident ray. Now, before you get excited, I know my arrowhead's on the wrong side. I'm going to fix that. And we'll make this green. Here is our incident ray. And that incident ray comes in, angle of incidence, 43 degrees. Okay. There is the reflection. Now, there are a few things you could be asked about for reflection more than just drawing. One of those is what happens to the wave characteristics. What happens to those big 6? So, of those we had frequency, we had period, we had speed, we had wavelength, we had angle, we had amplitude. So here, for the reflection up top, this is your tar, but this is the TA. Reflect is what we're going to focus on up here. For the reflected ray, all of these will remain the same. Remain the same. Except for the amplitude, which realistically decreases, although you don't often get asked about that. Now, being that we have the drawing here, I know the directions don't say anything about it, but you could actually see if there's a refracted ray we can draw. Yes, so now we're going to look at this boundary point. Go back to our tar. We're going to focus not on the reflect, but we're going to focus on the transmit. And it transmits in the form of refraction because we're going to a new medium. The important thing to realize with your arrowheads is it follows the general trend of where it was going. So roughly speaking, this should head off into maybe what you would call with the normal line of the boundary, quadrant 4 over here. You have to find out exactly where it will go though during refraction. You do that with Snell's law. So let's do real quick Snell's law. I'm just going to jump straight to the substituted. So, actually no, I'll give you unsubstituted. N1 sine theta 1 equals N2 sine theta 2. Please make a decision ahead of time. and 1 sine theta 1, we can make that for water. And 2 sine theta 2, we can make for air. And so you plug this in, of course, go check out your reference table chart to find the indices of refraction. Air is 1 even, water is 1.33, and so N1 is the water, 1.33 sine 43 degrees, it's the angle in water, equals 1.00 sine, we want the angle, theta 2, and when you solve this you will get theta 2 equals, the audience says 64 degrees. Did you use 43 to plug in? Do we have confirmation? Well, before we answer this, this actually could be a multiple choice question. Before we even answer this, what should happen to all of these? Let's list them out right over here again. Before we even answer, we had same group, frequency, period, speed, wavelength, angle, amplitude. Now if you don't recall what to do, a nice way to think about it is thin to thick or thick to thin. We are going from water to air, which would be thick to thin. A couple ways to think about this. Easiest in my opinion is, well, what's going to happen to the speed? If you go from thick to thin, light can now go faster, speed increases, and what goes with speed? The wavelength and the angle. The frequency and the period, if you remember, we said stay the same. So be careful. You can have a nice picture all set up and they say, oh, what goes on with the period? Nothing. The period stays the same. Amplitude realistically decreases. Again, you don't get asked about that too much. So if the angle is going to decrease, this thing is going to move away from the normal. In fact, you don't even necessarily have to do this with a ruler. I know for certain that it would go this way, roughly, and now it should go somewhere more like this way. This is another one of those thick to thin, the same thing we call high to low. High to low, away we go. So, we figured it out, came out to, what do you say, 64 degrees? Do we have confirmation?
Yes. Yeah.
We have to actually try it. 64 degrees, and you bring your protractor over here, line this up, and you should be 64, but you have to count. 64 degrees should be counted. Don't go to 64 on the protractor. Count 10, 20, 30, 40, 50, 60. 1, 2, 3, 4. There's the dot. I don't have to turn my protractor, but you do. Put your refracted or your transmitted ray in the direction of that 64 degrees. And refraction will make that from red. And there you go. And so here, the angle of refraction, which does not have a symbol in the reference table, theta refract, is 64 degrees. Okay, good. Now, one thing you may be asked to do is sketch the wavelengths, the wavefronts on there. So if you have to sketch the wavefronts without a scale, let's just sketch some wavefronts on there. We can pick our starting wavelength for the water. Maybe we'll pick something like this. Now we're in water over here, so it should be the same. But here we go to air. And what we said was when you go from thick to thin, it speeds up, the wavelength increases. That means that spacing has to increase. So if you're asked to sketch this, make sure you increase your wavelength. So instead of that same spacing, spread it out a little more, make it obvious. Let's not worry about scale here unless they tell you to worry about scale. Here the wavelength has increased. Good. Okay. Next one. Let's go over to water and crown glass. So we are going from crown glass to water. If we are first doing a reflection, same business as before. This is your incident ray. You're going to need a normal line. I will clone my normal line and drag it over. You actually have to draw one, sorry. So there's a nice normal line. And we need an angle of incidence. As usual, you have to measure the angle of incidence relative to the normal line. So, you come over here. This is your angle of incidence. Count 10, 20, 30, 40, 50, 60, 1, 2, 3.
Wait, can you make
63.
62 because I wrote 62?
You can make it 63.
Yeah, but I already did on the word.
It looks like 63.
I did 63.
Doesn't matter. If you get 62, I'm glad if you're hearing this at home. If you get 62 and I get 63, it's okay. You can do your refraction, your reflection, all that, still okay. Within an angle, a degree, 2 degrees, you're fine. Now we know the reflected ray must be also 63, but 63 from the normal. 10, 20, 30, 40, 50, 60. 1, 2, 3 is right there. So draw your reflected ray right in the direction of that 63. There it goes. And make this one blue. Angle of reflection, 63 degrees. Now, we can go through the same conversation we had before, which was from the TA reflect part of this. What happens to each of the individuals? Frequency, periods, wave speed, wavelength, angle, amplitude. All of these remain the same. We're in the same medium. Realistically, amplitude goes down. We're in the same medium. Okay, now we're going to try to go from crown glass to water. Now this was set up for reflection. Let's see if it works for refraction. Maybe, maybe not.
I got 90 degrees for my refraction.
Well, let's check it out. So if we're going to check out now what happens up here, now we're going to look at the TAR. Now we're going to focus on the transmit. And the transmission to a new medium is what we call refraction. And so there are certain things we should know immediately. Frequency, period, speed, wavelength, angle, amplitude. All right, so we are going now from crown glass to water. If you're not certain, check it out. Crown glass is 1.52. Water is 1.33. So you can even write it next to it if you want. 1.52, 1.33. So we are now going from thick to thin, which means, yeah, this is also what we call high to low. And so, speed will,
Increase.
speed goes up, wavelength goes up, angle goes up, frequency and period both remain the same. So we know that this should, instead of going in this rough direction it was going, it's going to come somewhere down in this direction. Now this actually could be risky business over here. We could be getting close to that boundary line. So if we run the numbers real quick, and our audience says this may actually happen, if we run our numbers, n1 sine theta 1 equals n2 sine theta 2. And so if we plug in ours, let's you make n1, we can make this the crown glass. And over here, we'll make this the water. By the way, it's nice to know crown glass to water. People sometimes get fooled into thinking everything is into air. All right, so N1 is 1.52 sine 63 degrees equals 1.33 sine theta 2. And if you solve for theta 2, so if you use 62, what'd you say, you got 90?
Yeah.
If you use 63, you're going to get error. So based on mine, this is actually an error. So this question would actually not be asked on a standard Regents question. The reflection part could be. The refraction part won't, because actually what you end up getting, this is a total internal reflection. So you may see a bonus question on that. But that part of it, let's put a big highlight on that. We'll highlight in yellow to slow down. This whole part of this question, slow down. This is bonus level. because it's a total internal reflection. All right. So don't get too concerned about that, the error problem that you have to deal with. Okay, good. So that one could be a reflection problem. Now, let's come down over here. We have these slanted boundaries. These are nice practice for us as well. In this one, we were going from water to air, and the assignment was to draw the reflection. So this one, you really have to pay attention here. You want to make sure that your normal line is perpendicular to the boundary. So, identify the boundary. There it is. Then, at the point where the ray meets the boundary, you need to draw the normal line. Be careful to set your protractor up with the boundary nicely. So that looks pretty good, right about there. And so now you need to make your normal line. Dot the locations. Let's set up our normal line. There we go. Now this, get out of the way, this is a proper normal line. Normal line should be perpendicular to that boundary. And so, the things you should start thinking straight away. You gotta be disciplined here. Where's my angle of incidence? The angle of incidence is from the ray to the normal, not to the boundary. The whole thing's rotated, so you might feel a little bit off. The angle of incidence is right here. There's your theta I. You have to count 10, 20, 30, 40. Looks like 45 or 46. What angle you get on this?
45.
Yeah? All right, let's take 40. Looks like 45 and a half. 45 degrees. Now you'll have a reflected ray that is also 10, 20, 30, 40, 5 right there. So you have to run through that location. Go directly from your point of contact through the 45-degree line. Mine's a little bit off. There we go. So now you have your reflected ray. Oop. This is blue. Doesn't want me to do it. Angle of reflection, 45 degrees. Now, again, all of the physical quantities, what do? They stay the same. So, if we come and write it again, during the reflection part of this, transmit, absorb, reflect, that's our focus on. The frequency, period, the wave speed, the wavelength, the angle, amplitude decreases. We're not going to worry about that so much. These all remain the same. Remain the same. Now we have to worry about what happens. Does this light ray actually transmit into the air? And so let's check it out. Transmitting into the air. Again, we are going from water 1.33, air 1.00. This actually is thick to thin, or high to low. These seem to be shaded that way, although the process is the same no matter what. Set it up. Roughly speaking, this piece of light is coming in this way, so it should transmit into this area, should follow that trend. And so here, N1 sine theta 1, N2 sine theta 2, make this the water, this the air, 1.33 sine 45 degrees. Be careful, you may have said 45 because they both are, but this is the angle of incidence, over here is not. Sine of 45 goes to 1, sine theta 2, and so the angle comes out to,
90 degrees.
what's your expectation? Look at them again for the, let's draw it over here. This is the transmit portion, absorb, reflect in form of refraction. Let's go in order we've been going. Frequency, period, speed, wavelength, angle, amplitude down here. So, frequency and period both remain the same. The speed will
Increase.
wavelength increase, the angle increase. So it would have gone somewhere over here. This is the angle. The angle should increase, meaning move away from the normal, should go somewhere over here. What'd you get? Angle?
70.
Confirmed? Okay. So we should get a 70-degree angle, which is not that easy to measure. Flip this around. Set this up. And count. Don't trust your reading of the protractor. 10, 20, 30, 40, 50, 60, 70. Oh, look, it's about where we guessed. Right over here. Don't worry about it if it goes over the lines from another problem. Turn your protractor and draw this through that spot. You can now have, stay over there. We now have our angle of there we go. Refraction, which is 70 degrees. Okay, so wave fronts again. Actually, we didn't sketch them on that last one, but this one we'll sketch them. The wave fronts. If the wavelength in water we can set arbitrary as this, then the reflection in water should be same thing. But when we go to the air, we're increasing our wavelength. So this spacing should increase. So if you just do a sketch of it, maybe you get something like that. All right, good. Last one on this sheet is this one from ethyl alcohol to glycerol. Okay, again, a funny boundary. Line up with your boundary. Draw your normal line. So our normal line now will run here. So there's our normal line. Post it all up so we get it there. There's your normal line. So your angle of incidence will be between your incident ray and the normal line, which is right here. Theta I. And don't trust, just count. 10, 20, looks like 8. 28 degrees. So, angle of incidence, 28 degrees. So the angle of reflection will be also 28 degrees. So we'll count on the other side of the normal, 10, 20, here's 8. And you rotate your protractor, sketch this in. Here's your ray, your reflected ray going off at 28 degrees. Your reflections in blue. So, the angle of reflection, 28 degrees. Okay. From the reflection, no surprise by now, maybe we could just start writing it: transmit, absorb, reflect, all the wave characteristics. Basically, the big six remain the same, other than realistically, amplitude decreases. All right, let's check out the transmit part of this. So now we're going to go from ethyl alcohol to glycerol. And so we should go check those out. Ethyl alcohol is 1.36. Glycerol is 1.47. 1.36. 1.47. Finally, we had 3. I was hoping there'd be 1. We had 3 thick to thins. Now we are going thin to thick, aka low to high. Good. Low to high. Now, it's still good to go back and approximate. This one would continue on its way. However, low to high was stay nearby. So if we actually look at, I'll run the refraction over here. This is the transmit portion, absorb, reflect. Well, if we look at all of them, the characteristics, frequency, period, speed, wavelength, angle, and amplitude. The frequency and period both stay the same. The wave speed now, low to high or thin to thick, it is going to slow down. The wavelength will decrease, the angle will decrease, and realistically the amplitude decreases too. So low to high was stay nearby, which means we should expect that it will fall somewhere in this region. Now it's just time to do the grunt work. Run the calculation. There's not too much space. We could squeeze it in right here. N1 sine theta 1 is N2 sine theta 2. We'll make this one ethyl alcohol, and over here will be the glycerol. So then when we plug in 1.36 sine 28 degrees equals 1.47 sine theta 2. Solve this, theta. I got 25.7. So we can roughly call this 26 degrees, which is not much different than 28 degrees, but it is different. So now, amidst all this mess, to flip our protractor around, bring it over here. Good. And we want to make our refracted ray. Keep in mind, we expected it to be somewhere over here, so we want to count 26 degrees in this direction. Change the color so we can see it among the red. 10, 20, 6 I think is right here. And so we have to draw our ray. Right through there. Good. So now our angle of refraction is 26 degrees. Look at all this. Let's move this guy out of the way. And so the last thing we can do on here is draw some wave fronts. If we were to do that, they're actually quite similar because the indices are close and so the angles are close. And so we drew wave fronts. Over here should be the same. And if you're just being qualitative, just a rough idea, this one we said the wavelength over here, the wavelength decreased. So these actually, though it's not nearly as extreme as I'll show it up here, you get a little closer together. And that is how this page is done. So all of you have access to this page because it is on the sheet, on the drive rather, right here, under your unit 8, going waves, going to the skill drill BQ8.3. And this was the, let's see, this was the sheet that had and going up into the right in order. So from the drive, it's not actually the first page, but the second page that we just went over. First page is very similar. We'll see. Maybe I'll put that one up too. But keep track of those trends. Those do matter.